Welcome to Weather and Climate lesson number 2, ladies and gents. I'm trying to do this in nice little bite-sized chunks because I do appreciate that some people get a little bit overwhelmed by this module. This is the second video and it will talk about why it's hotter at the equator than the poles and begin to look at atmospheric circulation and why we need that. Okay. I don't think it's going to be news to any of you if I tell you that it is hotter at the equator than it is at the poles. I think that's fairly obvious and we can look at it in pretty pictures. Oh, sorry, why is that not working? Oh, there we are. Or we could look at it on a graph. And I appreciate some of you might be like, oh gosh, but if you really look at this, look, here we have the latitude, here's the equator. Here are the poles, they're 90 degrees north and south. We have more insolation, remember that from video number 1, more heat coming in than going out. So we've got surplus heat at the equator, we've got deficit at the poles. It's hot at the equator, it's cold at the poles. But we need to know why. Okay, that's our important question. And it's not an easy answer, I'm afraid. Now, I have included this diagram in your module booklets and you might want to do some colouring or some measuring of what I'm about to tell you. The first part of the explanation is to do with the depth there and the depth there. I'm terrible at drawing, you know this, but if you can imagine that those rectangles are beams of sunlight. They are beams of insolation coming from the sun. You can either just tell from looking at the diagram, trust me, or actually measure, and I don't care which. Notice that this is much further than this. There is a greater depth of atmosphere at the poles than there is at the equator. And if I could just briefly take you back to this diagram, in video number 1, we talk about insolation and we say as insolation comes through the atmosphere, all sorts of things happen to it. And actually, on average, only about half of it ever makes it to the Earth's surface, i.e. insolation gets lost as it passes through the atmosphere. Well, if you take that idea, if you have got further to travel, more of the insolation is going to get lost. If you don't have as far to travel, more of the insolation is going to get to the Earth's surface. That is explanation number 1, depth of atmosphere. Explanation number 2 refers to surface area. And that area there is much bigger than that. I've tried to represent that with these cylinders. Possibly they're confusing or just not very helpful, for which I apologise. But I'm trying to represent that this is a huge surface area and this is much smaller. Part 2 then is the insolation has a much bigger area to heat up here than it does here. It's much more concentrated here, which is going to make it hotter. But if we link number 1 and number 2 together, less insolation makes it to the Earth's surface because there is a greater depth of atmosphere, and when it gets to the Earth's surface it has this huge surface area to heat up. It's going to be much colder. Here, more of the insolation makes it through the atmosphere and it's got a much smaller area to heat up. Okay, so part 1 of the explanation is depth of atmosphere, part 2 is surface area. Part 3 is albedo. If you think about the kinds of colours that you're going to get near the poles, they're going to be snow and ice. It's going to be pale colours. If you think about the kinds of colours that you're going to get near the equator, they're going to be much darker. So again, I'm just going to link back to last lesson. These are the kinds of colours you're going to get near the poles. These are the kinds of colours you're going to get at the equator. So that means that at the poles, most of the insolation is reflected, whereas at the equator, most of the insolation is going to be absorbed. Number 1, surface area. No, sorry. Number 1, depth of atmosphere. Number 2, surface area. Number 3, albedo. And finally, good news, number 4, length of daylight hours. We will come back to this in future videos, but for now, the closer you get to the poles, the more extreme your length of day and night becomes. Reykjavik, which is quite far north, but not at the poles, you can see that they have really long nights and really long days. But let's look at Alert in Canada, which is a military base, I believe. From the middle of quite early April till very early September, it's constant daylight. From the middle of October to the end of February, it's dark. It's really, really extreme. And even that is not quite at 90 degrees. It's not quite at the poles. So what we're saying here, ladies and gents, is this would be like turning the heating off from the middle of October to the end of February. There is no insulation being received at all. It's not the most important factor, but it has a part to play. Some of you might be thinking, well, hang on a minute, Nikki, surely the 24 hours of darkness that you get in the winter is cancelled out by the 24 hours of daylight you get here. But no, because even when they have daylight, remember, depth of atmosphere, surface area and albedo means it's going to be cold. Okay, now you have access to this PowerPoint on Office 365 if I teach you. So you can open these videos. They're not crucial actually. They're videos of what it might be like to have midnight sun, i.e. 24 hours of daylight, and 24 hours of darkness. So that's it. Okay, it's hot at the equator, it's cold at the poles. We have been through the 4 reasons for that. But what you then have to think about is fundamentally it is still too hot at the equator and too cold at the poles. And what we need is to mix that up a bit. And that brings us, ladies and gents, to atmospheric circulation. We need some of the heat from the equator to go to the poles and some of the cold from the poles to go to the equator. We need to mix it up. And that brings us back to the good old process of convection. The last time we looked at this would have been in tectonics, where we talked about why do the plates move? What is it that makes these enormous lumps of Earth's crust move? And it's all about convection. Well, we're back there again, ladies and gents. And what it leads to is this delightful thing called the model of atmospheric circulation, the tricellular model. It's got all sorts of different names. It looks terrifying. And I'm properly going to explain it to you in the next video. But for now, look, it's hot at the equator, hot air rises. It's cold at the poles, cold air sinks. Then, because it's convection, the arrows all chase each other. And suddenly, it's not quite as scary as it was before. And the most important thing to take from this video is the reason it happens is because we need to take some of the heat from here, some of the cold from here, and we need to mix it all up a bit. Okay, well done. You've survived video number 2.